Welcome to the first vodcast for Chapter 8. Chapter 8 is the last chapter that we will cover in thermodynamics, so we're on our last section. I was taking a look at the Moodle page, and let me flip over here so you can see that. Okay, I was taking a look at the Moodle page, and we have the due date for the Chapter 7 homework, which in 2018 will be Friday, April 20th. Then the last homework that we'll have is the Chapter 8 homework, which will be due at the time that you take your final exam. So we'll have approximately 3 lectures on Chapter 8. I'll post the homework assignment as soon as possible, and we'll go from there. All right. So let's flip over to the document cam and start talking about what's going on in Chapter 8. Well, Chapter 8 is nothing new. All right, so that's the good news. Chapter 8, we're going to bring together a couple of ideas. And the topic of Chapter 8 is a made-up word called Exergy. All right, Exergy it's a made-up word, but it's not a made-up concept. So the concept is something that we've already discussed. The first law tells us that energy is conserved. And so if we look at things such as thermal efficiency in terms of the first law, we look at the energy that we get out, or the energy that we are seeking, over the energy that we have to pay for, or the energy input. And because we are using as a basis of comparison the energy that we put into a system, we're somehow implying that the basis of comparison is all of the energy that we put in. So this basis is total energy in. Right. Well, when we began studying the second law of thermodynamics, we found out that while energy is conserved, we also find out that we always lose some energy. And we lose energy in a couple of different ways. We lose it to the environment, and we lose it due to irreversibilities. So the irreversibilities, to some extent, are engineering consideration. But the environment is nothing that we really have an option to change. And what I'm talking about by what we're losing energy to, we don't really lose it. We know exactly where it went, but we can't do anything with it, right? If you put heat into an engine and you generate work from that engine, you will be expelling heat to the environment. And if the environment is, say, at 70 degrees Fahrenheit, you could theoretically take this Q sub L and run a little engine, and if I could expel heat to a lower temperature, let's just say at negative 100 degrees Fahrenheit, and oddly enough, if I was at negative 100 degrees Fahrenheit, I could still expel heat all the way down to absolute zero. And every time this happens, I have a theoretical amount of energy lost to the environment. Because to explain this in another way, and a more chemical way, every time that you expel, like if you have a car and you have exhaust coming out of the tailpipe of the car, assuming that you have completely combusted the gasoline or diesel fuel, if any time that your tailpipe is expelling gas at a temperature above the environment, there's an amount of work that you're losing. In other words, if you could take the exhaust and get it in perfect thermal and mechanical equilibrium with the environment, you would have gotten all of the energy out of that system that you possibly could have. You would take all that heat and all the heat that you were able to and turned it into work, which was what the point of the engine was to begin with. But if you're above the temperature of the environment, you could have gotten more energy out of that system. Well, it stands to reason along those lines of thinking is that if the energy of the environment, the temperature and pressure, for example, were at a lower state, you could have gotten more energy again out of the engine. And you just can't help but lose. You can't get around that. It's not an engineering concern. You can't go below zero. You can't get, if you get below equilibrium with the environment, you have to feed it energy in order to do that. Okay? So all you can do is to get into equilibrium with the environment, and if the environment is above absolute zero, you're still losing energy. So when we talk about this, when we discuss exergy, we are going to define this term. It's more of a second law availability. And the best definition for exergy then, another word that I like better actually, it used to be called availability. And what that is the maximum useful work that could have been done or that could be done by the system at the given state of the surroundings. So what exergy is more of a comparison to the energy that was available to us based upon the environment. So in other words, if we eliminate all issues of irreversibility, how much energy could we have gotten, right? So we're not comparing it to this maximum, not even theoretical, but the maximum energy that we put in. We're recognizing that because of the state of the environment, we were going to have to lose some of the work to the environment, but all we can do is get into equilibrium with the environment, and all the work that we can get out is the difference between what we're getting, what we're putting in, what we're paying for, and what we have to exhaust to the environment. But we are assuming that that exhaustion to the environment is in total equilibrium. So if the environment is at 70 degrees and 1 atmosphere, the exhaust is at 70 degrees and 1 atmosphere. We're not losing anything above that. You know, we're not just letting it cool off in the atmosphere and losing that energy. So it's how much we could have gotten if we would have had a perfect world, but the perfect world still had an environment. So in some ways, this is a second law concept, isn't it? We're validating the idea that we never had the opportunity to get 100% of our Q sub H out to begin with. In other words, the only way we can get all of our Q sub H out, we showed with our efficiency or our thermal efficiency equations, is if we have a completely reversible machine and if we expel our exhaust to absolute zero, or Q sub L is 0, T sub L is 0. So this says, okay, well, we do have a perfect machine, but we still have an environment at some temperature and pressure. All right, so in some ways, in a very profound way, exergy, or availability, which those two words are interchangeable. That's why I have this equal sign. It's actually a definition. Okay, so this should just be a regular equal sign. But exergy and availability, those two terms can be used interchangeably. Exergy is the term that's more modern, and when I say modern, since like the 1950s, so it's been a while. It's been around a while, but availability is still recognized as the same idea. It's going to tie very closely into the idea of reversible work. If we had a perfectly reversible system, how much work could we get out of it? So what do we always know about reversible work? Well, if we're trying to get work out of a system, that the reversible work is always going to be greater than the irreversible work that we could get out. Because we're always losing something to friction, we're always losing something to systems that are not operating in an optimal fashion. But the reversible work is always going to be the maximum between two states. So reversible work is also defined as the maximum useful work that could be obtained by a system between two states. Okay. Now look at the relationship then between exergy availability and reversible work. They're very similar. They both talk about a maximum amount of work that we could have gotten. The only thing different is what our discharge state is. Okay? Here we're talking about discharging to the environment. Here we're just talking to discharging to some random state. So in other words, reversible work, if your discharge is to the environment, is exactly the same as availability or exergy. All right, so one thing that's interesting here then is that the units of exergy which is given by this symbol capital X, and the units of reversible work are the same as the units for actual work, which might be foot-pounds, which might be Newton meters, which are joules, or which might be BTUs, or any variety of other inch-pounds and so forth. But the units of exergy, reversible work, availability are all the same. We can also write this in terms of rate. So we can talk about rate of exergy, which can be designated by the single x dot, which is going to be work per time. So for example, Newton meter per second, which is a joule per second, which is a watt. So the rate of exergy is going to be the same as power. So it's the rate of work. So it's the same kind of an idea. One of the more confusing things about this idea of exergy is the fact that a lot of the words that we use and a lot of the concepts are very similar to each other. So it becomes a little bit confusing because, not because they're very different, but because they're very much the same. So there's a lot of crossovers and there's a lot of places to think, wait a second, am I talking about reversible work? Am I talking about availability? Am I talking about exergy? Wait a second, is exergy the same as availability? Is useful work the same, and so forth? So there are just some places where you can get a little bit confused. But my advice to you is to take good notes, of course, when you do your exam, And the other is to keep coming back to this exergy, because exergy is the overarching topic. And so everything else is sort of a derivative of exergy. All right, so when we talk about the difference between the actual work that we get out of a system and the exergy that we could have gotten out of a system if the world was a perfect place, we are talking about irreversibilities. And once again, this idea is built up between actual work and exergy. And we identify this with the letter I. And it is the difference between the reversible work we could have gotten between two states and the actual work, or what we call useful work, that we actually did get between the two states. Because the reversible work minus the actual work is going to be the irreversibilities, or the amount of work, the amount of energy that we lost to irreversibilities in the system. And once again, you can see that irreversibility is going to have the same units as work. And also that we can talk about rates. So you can talk about a rate of reversible work, which would be reversible power, minus the actual useful work rate is equal to the rate of irreversibility.
Can we refer to irreversibility as just like energy loss?
Yeah, well, there you go. You're cooking with gas. That's right. We're almost there. We're going to talk about this other, what else we can refer to it as is exactly correct. So if we want to relate irreversibility back to exergy, which exergy was the amount of work we could have gotten, or the reversible work if we were discharging to the environment, right? Whatever else we had, we could also, if we want to think about irreversibility in terms of exergy, we can talk about it as the amount of exergy that was destroyed. So in other words, we could have gotten this much out, and yet we didn't due to irreversibilities, so we had exergy destroyed. And we can also refer to that as lost work, which to me is the best term. And like I said, it's not really lost. We know exactly where it went. In all of these things, energy is conserved in the broadest sense. It's just we can't use it. So it was lost to us. It wasn't lost like going, we know where it is, but we can't do anything with it. So it was lost to us.
So it's referred to as destroyed exergy because it was no longer useful work.
That's it. It was like you talk about, okay, I could have had this much. It's exergy is a different theoretical standard. When we talked about the first law, we just talked about the amount of energy we got out of how much we put in. And then we started talking about the second law. We said, wait a second, we never really could have got this bottom stuff out. So how much could we have gotten out based on the second law? That's our exergy. And then exergy destroyed is how much we didn't get out due to the irreversibilities of the system.
Okay.
Yeah, super. Yep, actually excellent. So to come up with a wordy definition for this, another thing they call it is wasted work potential. Maybe I'll go and put asterisks over which of these I prefer, which ones of these terms. Wasted work potential, it's descriptive, but it's kind of wordy to me. Okay? And that would be based on irreversibilities, of course. So what this implies if wasted and lost are kind of the same, work potential is really kind of exergy, isn't it? So in other words, even though this isn't a great term for it, we could also say exergy can be thought of as work potential. Okay? So all of these are sort of tied into the idea of the second law. We're immediately recognizing that we couldn't get something out of the bottom of that system. When I say bottom, I mean the ejection phase, the ejection cycle, or the ejection stroke, or that we're losing something to the environment. Okay? So this ties into the idea of how much could we get. And this is, we need to define one more concept. And then we'll just talk about this a little bit, which is called the dead state. Sounds like a Stephen King horror novel, right? Like The Dead Zone or something like that. But what that means is when something like the exhaust phase, when a system is in equilibrium with the environment. Okay? That means that everything below that in terms of thermodynamic state is not available to you at all. Okay? So if the temperature outside is 70 degrees Fahrenheit, which is wishful thinking on my part today, and 14.7 psia, that means if you run an engine and you discharge and all of your exhaust stream is at 70 degrees Fahrenheit and 14.7 psia, that means that you have got all the energy out of this that you can. You've done all of the work that is possible. I mean, now we're not considering irreversibilities. We're not talking about availability, right? We're talking about exergy minus the irreversibilities, okay? But we have gotten all the work out of it that we could have given that machine operating at that state. If you discharge your exhaust and the atmosphere is at 70 and 1 or 14.7, and you discharge and your exhaust is at 110 and 1.2 or 16 psia, there's still some more energy. That fluid is going to have to lose energy as it comes into equilibrium with the environment. And you could have gotten that energy out in a perfect world. So this, whatever the environment is referred to as the dead state. And it is sometimes subscripted with O's or zeros, P naught, T naught, meaning that's as low as you go. Now, the dead state, there are standard types of conditions that are associated with the dead state. But the real answer is the dead state is whatever the environment is at, okay? But usually they'll say like 70 and 14 or 20 degrees centigrade and 1 atmosphere or something like that. And they'll tell you what it is, and if they don't, you can make an assumption about what that would be, all right? So does that also imply that engines could run better in colder temperatures? It kind of does, actually, if you think about it. If you could discharge your exhaust to a lower temperature, you could theoretically get more energy out of it. There's more of a delta T. So, but it's theoretical because everything's computerized. It's set up to run under certain specs. So, yeah. That was a bad question. I shouldn't ask that, but but anyway. So, we've talked about the idea that exergy is given the symbol X, capital X. And we've already used little x for steam quality. So we use X dot, okay, for rate of exergy. And sometimes we use a little x sub PE or little x sub KE or little x sub U. This would be for potential energy and so forth. But when we talk about the exergy of a system, we go to a different set of variables, which can also be interesting. And one of them is phi, and one of them is psi. And don't you just love that? So psi, refers to flow exergy, and phi refers to, well, they don't even use that here. Huh. That's a change from the last edition of the book. So we're just going to use psi. All right. And they use it for both. All right. Well, there you go. So flow exergy or non-flow exergy. Does not seem like an improvement to me, but there you go. Nobody asked me. All right. So if we are talking about non-flow exergy, we can say that this is equal to U minus U0, which is the dead state, plus P0, dead state, little v minus little v0, minus T0 times S minus S0. I'm going to go over these terms with you in just a moment, plus V squared over 2 plus GZ. And for flow exergy, we're going to say that this is equal to H minus H0 minus T0 times S minus S0 plus V squared over 2 plus GZ. All right, now the first thing you notice is, it's strange to me, but I'm going to never mention this again, that we use the same variable for each of these. So flow exergy generally refers to a control volume where we have fluid moving in and out of something, or fluid moving in a pipe, because what we're really talking about here is a particular state. So if we have fluid in a box, for example, we could measure its internal energy, its specific volume, its entropy, its velocity, and its height. So this is the exergy associated with potential energy, or we could say potential exergy, because what's my Z sub 0? It's 0. It's whatever the datum is. Here, this would be my kinetic energy, my kinetic exergy, and once again it would be V minus V0. The dead state for velocity is no velocity at all, so it would be 0. That's why we don't include it. And here we have this T0 S minus S0 term. We know from our previous discussion on the second law that del Q over T is related to the change in entropy, and that del Q then is equal to TdS. And so if T is constant, we can say Q is equal to T times delta S. So this is related to the heat if we were discharging to the dead state. P times specific volume change, P times V, if you remember, del W is equal to P dV. So if we integrate both sides, if P is constant, we get the work from 1 to 2 is equal to P times delta V. And on intensive basis, in other words, if we divide both of those by the work, we get P delta little v. So this is a boundary work term or an expansion term, and this is an internal energy term. So we could refer to this as the exergy associated with internal energy, the exergy associated with boundary work, the exergy associated with heat or with entropy, the exergy associated with velocity or kinetic energy, the exergy associated with position. Now when we talk about flow, you notice these terms, these last three terms are identical to each other, but instead of U minus U0 plus P times little v minus V0, we now have H minus H0. Right? Well, H, enthalpy, is defined as U plus PV. It's a definition. So if you look at that, we could think about this as being U plus PV minus U0 plus PV0. And if you distribute this and rearrange, you'll see that these two terms are actually identical. I mean, these two terms, what I mean to say, these two terms actually it's three terms, this expression, make it more general, this expression is identical in value to this expression. Okay. All right, so at this point, do you have any questions? All right, well, let's call it quits for today. This will be our first video. I'll do either one or two more videos on this chapter. We'll do some homework problems. I'll post the homework, and I'll post the problems and so forth, but no official homework for tonight, except for it would be really useful if you would read through this material. If not reading the whole chapter, at least if you read the summary at the end of the chapter, and maybe just keep careful notes about not getting the terms confused. All right, we'll stop streaming. Have a great day.